Yeah, thank you. And I mentioned earlier to a friend, but you know that you're among a bunch of passionate people when they show up to talk about probabilistic programming at 11 o'clock on a Sunday. So I'm very grateful to everyone for being here. This talk is called Probabilistic Programming in the Real World. The intention is to expose probabilistic programming to someone who's maybe not familiar with it or is lightly familiar with it, hasn't dealt with it in industry, and wants to know what kind of problems can I apply this to, what's the way that this works under the hood. A quick couple of public service announcements. So first off, thanks to Capital One for hosting us. This has been an excellent conference. Also, Travis Oliphant yesterday mentioned you should support NumFOCUS, and you should. So I wanted to put that out there. If you are not a sustaining member, it's not very expensive, and a lot of us, including myself, owe our careers to NumFOCUS. So I would encourage you to please, if you aren't, or even if you are, to throw some money toward NumFOCUS. And finally, I am on the organizing committee for a machine learning conference that is taking place in April called the TomTom Applied Machine Learning Conference, or AMLC. So two things, you should definitely go to that conference if you are going to be in the area. It's going to be in a movie theater. So we have theaters that we rent out downtown Charlottesville, and we bring in about 500 people to come watch machine learning talks in movie theaters. And you should also give a talk. So our RFP is open now, and that's a link that you can't click on. But if you just search TomTom AMLC, I'll also put these slides, make them available, and that will be a clickable link. I think that's open till the end of December. So if you have something kicking around, please go ahead and submit. A little bit about me. We already went over, but I'm a lead data scientist at S&P Global Market Intelligence in Charlottesville, Virginia. I work on a web platform for financial professionals. And I focus primarily on problems in search, so natural language processing as it applies to getting people to the content they're looking for within a very wide and subject-specific domain. I am passionate about solving problems and hanging out with my wife. Her name's Kylie, and our dog, whose name is Boolean. So I want to get started with sort of a toy example that is not toy to me, because I think about this a lot. How funny is my joke? So the joke is, why did the chickens studying machine learning cross the road? And the punchline is, the answer is trivial and is left as an exercise to the reader. So if you're gonna rate this joke on a scale of 1 to 10, who would give this a 7 or above? Who would give this between 4 and 7? And who would give this between a 1 and a 4? Right. So that's probably about what I expected, but let's play this out. So if we assume the joke funniness ranges from 1 to 10 on a continuous scale. So we're not discrete. We can have partial rankings. Joke funniness is truncated normal. So we'll have a normal distribution around this scale, but obviously we can't go above 10 or below 0. And if we don't have any expectation for a given joke's funniness a priori, so I can't come in and say, well, my jokes are typically around a 9, so that's what we expect this one to be. In that case, we can actually make a model and say, well, given observations that I make around people rating my joke, how funny can I expect my joke to truly be? And so this is some ratings that I got hanging out around Charlottesville. I asked 4 people. I got 3 4s and a 3 on that joke. And this is a PyMC3 model that I'll walk through for everyone. As a context manager, if I say with this model and I give it a name, just a reference, joke model, I need to define priors on my truncated normal distribution, which is going to describe this joke. So I'll create a uniform distribution over the mean of the joke, and then I'll just go from 1 to 10. So that's a completely non-informative prior, doesn't bias me toward anything high, low, or medium. And then I have a standard deviation of my funniness, and that's going to be a half Cauchy distribution, mostly because that tends to make sense in standard practice, but half Cauchy extends really far to the right and cuts off at 0. So half Cauchy can't go negative. And then when I define my funniness, I'll say my observed funniness is a truncated normal distribution. It's got a mean that's defined by this prior, a standard deviation defined by this prior. It can range from 1 to 10, and I observed these 4 elements. And the beauty of probabilistic programming is that's essentially all I have to do. And it's all in Python, and I can click what's called the inference button. People usually put a trademark on this when they present it at PyData type talks. So it's the inference button TM. And I can essentially say, well, we'll get to what all this code means, but it essentially doesn't vary for any probabilistic model. But I can say, given the model that I've defined for you and the data that I've observed, distribution from the posterior. Let me sample from that posterior distribution so I can see the values that I care about, namely the mean funniness of this joke. And give it back to me as a pandas data frame, and then let me go plot it in this case, bokeh, which is really cool. And I can see, given that my mean funniness for this joke tends to be around 4. And this is a computationally derived sample from the posterior distribution, given the model that I laid out and the observations that I recorded. And so you can see this doesn't match any distribution you would find in SciPy. But it is directly from the posterior with support for uncertainty. So I can also compare that joke between audiences. So let's say I've got the same joke and I recorded a few different observations. So I've got the ratings at home, I've got some ratings at work, where it seems to do about the same, but I got more people to answer my joke at work. And then at PyData, outside of this particular talk, this joke did pretty well. So I got some 7s, 8s, and 9s. So now I can basically take the exact same model, except now I'm just going to define it 3 times. So I'll say mu funniness home, mu funniness work, mu funniness PyData. These are all going to be the exact same priors defined now 3 times with 3 different names. And I'm going to do the same thing with this model. I've got my observed funniness at home, at work, and at PyData. And I just map these same standard deviations, these mu's, and I go ahead and find my map. Click the inference button. This is the exact same slide as I showed you before. And I get my same pandas data frame. So this doesn't make sense by itself. These are each individual samples from the posterior, which we're going to talk about in 1 second. But you can think of them as specific simulations given the model, given the data, for all 3 of those sample distributions. And then I can compare my home distribution versus work. If you recall, I have a few more observations at work, and we can see that those actually warp the prior much stronger. So I'm almost certain that it's about a 4 with my work colleagues, whereas at home, it's not quite as clear. And then at PyData, it seems to be shifted pretty far rightward. So I'm pretty sure the joke lies around the 8 line. And then you see, because we squish in this truncated normal distribution, we can't go past 10. We get sort of a spike at the end. So there's some likelihood that it's a 10 joke, really. What else is really cool is that I can do posterior integration. So, interrogation. So given that I have this pandas data frame like any other pandas data frame, I just plotted it like any other, I can go do some summary statistics on it. So how confident can I be that my joke will do better at PyData than at home? And that's just really a summary stat count over this data frame. So I can do some data frame method chaining and say, I want the incidence that it's funnier at PyData than at home. I'm going to sum those all up and divide by the length of the data frame. It's about 80% confident that this joke does better at PyData than it does at my house. And by the same token, I'm over 90% confident that joke does better at PyData than it does at my work. And that's despite the mean of those ratings actually being identical. So this is purely due to the increased confidence that I gain from additional data collection. And because I have full support for uncertainty in a probabilistic model, I can show exactly what I expect the range of that to be. So this is what I would call a joke of a model. It fits fairly well for a simple rating, but the real interesting part of this question comes not in defining the model, or not in interrogating it, but in saying, what's the right way to structure this formula? Because what if you would say, probably defensively, that jokes don't really range from 0 to 10. Jokes are binary. You either laugh or you don't. Well, then it turns out you can define a model for that. You could treat it like a Bernoulli trial, and you could say, what's the hidden probability that my joke will get a laugh or not? What's the weight of this coin? So a couple other questions. What's the probability that a random person finds my joke funny? How many times can I expect to tell this joke before I get a laugh? How sure am I that this joke is better than another joke that my friend told me with the same audience? All of these questions are fully supported transparently within probabilistic models. And the answer to them is left as an exercise to it. So now I want to talk a little bit about theory behind Bayesian modeling. This was a sticking point for me for a long time, and so I'm hoping that my suffering can lead to your enlightenment. So I think everyone's familiar with Bayes' theorem, but the labels that we apply to it are important. So we've got probability of B given A equals the probability of A given B, which we call the likelihood, times the probability of B alone, which is our prior, divided by the evidence, which is the marginal likelihood, and that all equals the posterior. So the posterior is, given this data and this model approach, what do we expect the values for the parameters of this model to be? And it turns out that this is a very intuitive tool once you get your arms around it, but it's actually really difficult to solve real problems using Bayes' theorem purely. And the reason for that boils down to the right-hand side. So we'll just take the numerator of this right-hand side, the likelihood times the prior. So we'll go through each of these individually. The likelihood, the probability of A given B, so that is the support for our chosen parameters given the data. How likely is this model given the data that we've observed? And you can do that pretty trivially. It's not that hard. So here is in Python using SciPy. Thanks again to Travis Oliphant, who you should all support as sustaining members of NumPy. So from SciPy.stats, import norm, and we can say for a given normal distribution, get the probability density function for some observed values. And then assuming that they're all independent, we can just multiply those together and we'll get the probability that those values get observed under that distribution. And all this happens sub-millisecond. And this is very easy to do. We can vary them, we can change the data, we can change the probability function, and we can see what we expect to be the outcome on the likelihood of the model given the data. Now, the marginal likelihood, so if we've got probability of A given B, then probability of A is just the integral of probability of A given B over all possible values of B. And it turns out that that is probably really hard. So for models that are even a bit more than trivial, calculating the marginal likelihood across all parameter values is generally not possible analytically. And that's outside of some special cases called conjugate priors. So if you restrict yourself to very constrained modeling choices, where I say, given this model in this parameter, its prior comes from this distribution. So, and I restrict myself to specific rules in terms of what chains into what, then I can sometimes analytically derive due to math tricks. But generally, you don't want to do that. And it's tough to make those choices. So numerically, you can calculate a single integral really well by summing up trapezoids. And then Fubini's theorem tells us that you can translate multidimensional integrals, so integrals over integrals, into repeated applications of a single dimensional integral, but that is exponentially complex. So if you start doing this, if you start translating multidimensional integrals into repeated single integrals, and you do it on your MacBook, it will start cooking eggs, and it will take very long. So we don't want to do that, and we need to find out a way around it. So let's look back at Bayes' theorem again, and let's consider for a single value. We know that it's calculating the denominator of this right-hand side is the difficult part. So for a single value, let's say B2, we think that's actually not that hard. So we can calculate the likelihood, we can calculate the prior just by virtue of having defined them. And we can do that same thing for B1. So for any two values, we can calculate the likelihood and the prior for B1, calculate for B2. We can also consequently calculate their division. And this leads us to Monte Carlo sampling. So this is an example of Monte Carlo sampling to find a circle, to sample within a circle. And the idea is that we're just going to select random points and then calculate how likely are they to occur under this model specification. So knowing the relative value of Bayes' numerator, we can randomly sample values for B in order to determine the shape of its posterior distribution, right? We can ignore this denominator if we can just find really good values for B and calculate how likely they're all going to be under the posterior. And we'll do that using this ratio. So we'll propose a sampling algorithm. We'll choose some starting value for B, call it B hypothesized B sub h. We'll compute Bayes' numerator for B sub h, and then we'll change it just a little bit. We'll add some epsilon to B sub h and calculate the Bayes' numerator for that. And if the probability, the likelihood of B1, right, the perturbed B sub h, is greater than B sub h, then we'll just say that's our new hypothesized value. And we'll just keep doing that until we get to the optimal value for B sub h. That seems like it'll work pretty well. But what that actually does is just create a hill climbing algorithm. We're just going to proceed in one direction until we get the optimal value, and then we're going to stop. And that doesn't actually solve any of our problems if we're trying to estimate the distribution of this posterior, because it's going to fail when we reach a local optima, and there's no support for uncertainty. We just have a single best value. So let's change this a little bit. Rather than just directly accepting b sub 1 if it's greater than b sub h, let's calculate if it's greater than 1, or if b sub 1 is greater than b sub h, we'll assign b sub h equal b sub 1. But if it's less than b sub h, so if it's less likely than b sub h, we'll still assign it to b sub h. We'll still accept that value with probability equal to b1 over bh. So if it's much less, we're probably not going to go there. But the closer and closer it gets, the closer it gets in likelihood to the value that we're currently testing, the more likely we'll actually just switch anyway. And what this does is, and last step is to profit. What this does is allow us to take non-hill climbing jumps. So I stole this image from ResearchGate. I think it's really good. But we are no longer proceeding directly toward the middle. We're actually bouncing around the outside. And so we're moving from to the tails, we're moving to the areas of high density. We're actually moving to the areas of high density at the exact ratio that those areas of high density are more likely than the areas of low density. And so this routine that we've proposed now satisfies the Markov property. So every observation is not dependent on the observation before it. It's memoryless. And so what we've done is created a Markov chain which at the long run assumes the probability distribution of that posterior. And the little trick here is that the ratio of Bayes' numerator for one value to Bayes' numerator for a different value is actually the ratio of all of Bayes' theorem for one value to all of Bayes' theorem for the other value. We've gotten rid of this really nasty integral, the marginal likelihood, and gotten away with a much easier computation that we can do computationally. So this is called Metropolis sampling. It came from John Metropolis in the 1950s, and it was designed to run on the MANIAC supercomputer. And the MANIAC name, I have it written in the slide notes. I forget the exact expansion, but it was a joke by John Metropolis. After UNIVAC and ENIAC, he came up with MANIAC, and we stopped doing all the EAC computers, and that was the end of it. So John Metropolis defined this in the 1950s, and it's the backbone of Markov chain Monte Carlo analysis. And there have been improvements since then. So in the 1980s, Hamiltonian Monte Carlo was hypothesized. So it includes an idea that we can have an analogy to momentum on a frictionless surface to inform steps in the Markov chain. So rather than having to sample randomly, we can remember the momentum, the Hamiltonian of our distribution, and much quicker converge to some value. And then fairly recently, Andrew Gelman and his team at Columbia came up with the NUTS, the no U-term sampling algorithm, which is how most of this is done today. So Stan, PyMC3, Turing, any probabilistic programming environment now uses NUTS. But the backbone of it is still Metropolis, and I think that explanation of Metropolis is really intuitive. So this is now a real superpower that we have. We have the ability to design arbitrarily complex nested models and then crank Bayes' rule until we come up with posterior distributions for each of the hidden parameters in it. We have the ability to impart expert knowledge onto systems and to values for those models. So we can say, well, we think that this system works this way, and we'll choose any prior we want for any value, and we'll choose any expansion of those priors that makes sense, including branches, including if statements, conditionals. All of that's now on the table. And we have the ability to derive for a given model structure a probability distribution for the values which drive that model structure. So I think the core of this talk is what common real-world problems, if we now have this superpower, what are areas that everyday data scientists should be applying them? And I have three ideas I'd like to posit. I think they're ideas that a lot of us run into pretty often, that I think they're solved superiorly. It is a superior solution to use probabilistic programming than more traditional methods. The first is model validation when test data is expensive. This is an increasingly common problem in the age of transfer learning when you train on really large available data and try to evaluate your model against scarcer domain-specific data. Also, systems that can be encoded with pre-existing expert knowledge. We find ourselves automating a lot nowadays. And generally, the people who have been doing those jobs know a lot about those jobs. And I think we do a disservice if we don't listen to them. And finally, problems that require reasoning with uncertainty. So if you want to talk about the potential impacts and the expected likelihood of impacts for some decision, Bayesian is almost always the way to go. So model validation when test data is expensive. Again, you have lots of situations where you're trying to train a model on, say, Wikipedia or some very large, readily available data set, and then evaluate and say, well, how does this model that I trained on really general data work on this really specific use case? And typically, that data is not as readily annotated. You don't have some test or dev set that people have gone and annotated for you so that you can test your model. And so a scenario that we've run into at S&P is if you're working on document classification, which we do a lot of. We process financial forms, so 10Qs, 10Ks, 8Ks, these are all forms that get submitted to the SEC that then we process and make available to our clients. So if you have a lot of documents like this, and let's say some of them are labeled and some of them aren't, but your populations aren't necessarily homogeneous. So we ran into a situation, we had 2 legacy systems. One of them was fully labeled going back several years, and one of them was not. So the first legacy system had performed better than the other one. And we had to assign labels to these new documents while being pretty sure that they didn't fit the same distribution as the old documents. And so we like to automate this. How do we do it? A little diagram here. We've got good training data. We want to train a model on that and then predict it on a totally new set of data that doesn't come from the same population. And this talk isn't about how we did that. This talk is about how we proved that it worked. So you've got your officer who's going to evaluate these predictions. And you can treat this like a coin flipping problem. So if you have a classifier, that classifier has some underlying likelihood that it's going to be correct. And what you're trying to do is determine what is the value of that probability that you get a heads, that you get a correct classification. And so if we observe a relatively small number of observations, and then we can define our model. So in PyMC3 syntax, we again just open up this context manager and say, with our model as success model, we'll define a prior on the P, the underlying probability of success for Bernoulli trials, as just a uniform prior. It informs no information. And we'll say, given our trials, if our P is, well, that's a typo, but if our P is the probability of success, then what's the value? What do we expect the value of that P to be? And we can come up with a full posterior derived distribution that shows it's about centered at 0.7 with support for uncertainty, so we know it could range as low as 0.3 or as high as 0.9. And then again, we can do summary measures on that accuracy. So pulling down our data frame with all of our prediction samples from the posterior distribution, we can say, what's the mean probability of success, and then what's what in this case is called a 90% credibility interval. So out of all these samples, and we did 5,000 of them, what's the middle 90%? And we'll encode that into an F string and say, well, the mean accuracy is about 65%, and the 90% credibility interval. And this is not a confidence interval because we don't have some sort of rationalization we have to do. It's like if we ran this 1,000 times, then we would expect 90% of those values to come within these range. It's really just, this is how confident we are. We're 90% confident it's going to fall in the range 0.4 to 0.8. And this has full support for uncertainties. So if we just go get more trials, we can narrow this histogram from the posterior. And that allows us to make a pretty credible argument to business stakeholders and say, well, if you don't really like this, then you should go annotate more data for us. So use case 2 would be systems that make use of expert knowledge. So a lot of times determining the correct structure for a graphical model is really hard. And that's where you spend the bulk of your time when you're building these sorts of models, is what informs what are intelligent priors for the different parameters that we're going to encode here. And a lot of times, the people who are best qualified to answer those questions aren't data scientists. So if you have a situation like we've had, where you're trying to improve some system where a manual worker consumes some raw resource and produces finished work, then you would really benefit from talking to that person. And if you suspect, well, I can just fit a probability distribution to each of these processes, then you're going to run into a situation where there's a little bit more complexity than you expect. So a lot of times we ran into this in search, where we were trying to model searches that people were running on our platform. It turns out that there are multiple types of searches. And if we just model them as one giant distribution, we're not going to get a very good result. And so in this case, we've got 3 different types of documents that this person is consuming. Then we need to treat them individually. And we can talk to them about what are intelligent priors to put on those documents as far as time to completion, level of effort, in order to complete their work and create this stream of finished documents. So here's a little bit more complex model. And this will be helpful to show off some of the syntactical tricks in PyMC3. But if we've got, let's say, a document rate, and it's deterministic, it can come from one of 3 documents. So we'll define a discrete uniform distribution which takes on one of 3 values, 0, 1, or 2, with no prior likelihood for any single document. And we'll define normal priors for the standard deviation and the mean for the parameter which drives the exponential of these documents. So this exponential is time to completion. It has one parameter, and that's going to be driven by the rate. So we'll have a normal distribution, and we'll define one of these for doc1, doc2, doc3. And by talking to the person who has done this process in the past for these different documents, they tell us the first type takes about an hour, the second type takes 20 minutes. So this will be the number per hour. And the last type takes 6 minutes. We can encode this directly, crank it through, and just by observing one document, we can get an estimate for what type of document was that, given the priors that we've gotten from our business user. And just by saying this took 0.3 hours to process, we can say, well, we're mostly certain that that's 1. That's the second document type, with about equal likelihood that it could be the first one or the third one. And if we can observe them taking on more and more of those types of documents and recording the time that it takes them to complete them, we can narrow this distribution. So we can say, with increasing likelihood, what type of document was this? The third type of problem that I think really lends itself to probabilistic programming is when you're reasoning about uncertainty. So a lot of times, a question that we get as data scientists is, should we make this change to our process? Given some improvement we suspect that you've made, what is this going to benefit us? What's it going to potentially cost us? If we make the change, what's the worst case outcome? What's the best case? And how sure are we that this situation will improve because of your adjustment? And an example that we've run into is number of errors. We have people who process documents, they make mistakes sometimes, and we want to minimize those mistakes. So a really important metric is the number of errors that they're making. However, it's really expensive whenever we put this model into production and have them executing on it in real time. So we don't have time to do a true A/B test. We just want to say, well, here's historical data, here's the new data. How quickly can we know that this is good or it's not? So what I'm going to show you is about 15 observations from old process versus 5 observations from new process, with one really high outlier here. So we suspect that these are mostly better, but we've got 122, and we want to know, does that represent some spurious outlier, or is that an indicator of a larger problem, and how certain are we of that? So we can take these data, we'll just mash them into a data frame. So we've got our value, we'll just concatenate those guys, and then groups. So old process and new process, those are just labels. And we are pretty sure that these are not normally distributed. They're heavy tails. And so a t-test here would be the way that most statisticians would go about doing this. We'll just do a t-test between the means. But that's actually assumes behind the scenes that these variables are normally distributed. And in fact, we're almost certain that they're not, especially when we look at this new process. So we'll encode our model here. This takes advantage of Unicode syntax. So we've got, with our model, again, going into the context manager, the group 1 mean is a normal distribution around just the mean of the first group. Group 2 mean is mean of the second group. We'll put in reasonable values for high and low standard deviation values. And we'll define a student t distribution for these values. So rather than taking a normal and computing the difference between these, we're going to use a t distribution which has heavy tails. It takes four parameters. So we've got the nu, which is a measure of normality, and we're going to take that to be really high, which means it's not going to be normal at all. The lower this nu value is, and we've got 1/30, the less and less normal this distribution is going to be, the more weight we put into the tails. We're going to assign the mu to the group 1 mean, which we calculated up here. That's a prior. The standard deviation is a uniform distribution from 1 to 10, and we observed the y1s and the y2s that we calculated here. And then we can also throw in a deterministic variable which says, there it is. We can encode a deterministic variable which is the difference of those means. So group 1 mean minus group 2 means, that's just going to be a tracker within the model that we'll continue to identify and then we can plot and do analysis with. So here's our distribution. The old process is in blue. The new process is in sort of this pinkish color. And we can see we're kind of sure that the new process is better, but there's a lot of uncertainty. It spreads really widely, particularly because we have very little data and one really high value. You can see it pushing out on the edge there. But we can still articulate exactly how sure we are. So we can show our difference of means, and this is just plotting that deterministic variable that we plugged into the model, and say, we'll throw a red bar at 0, and the bulk of this distribution is greater than 0, so we're pretty sure we're going to have fewer errors. And exactly about 75% of our posterior simulations had fewer errors in our new process than our old process. And this is a much more persuasive argument than, with this histogram, than just this number. Being able to say, well, here's the exact range of values that we expect to achieve from the posterior distribution of this model. So I'd like to talk a little bit about where I see probabilistic programming for the modern data scientist stack. First off, I think it's ideal for treating uncertainty as a first-class citizen, which I think is a requirement when you're adjusting business processes. You have to be able to articulate how uncertain are you, and what are the best and worst cases scenarios. Also, you need to transparently specify any of your assumptions. I think too often we make modeling decisions that have assumptions buried behind the scenes and then don't transparently interrogate what those assumptions are and whether or not they fit our data. But when you are articulating a model completely in Python to share in front of the world, you don't have that option. You have to say exactly what your assumptions are and how well they fit. It supports online updates, so online learning becomes increasingly in demand. A lot of what I would call a cookie cutter machine learning model, like what you'd pull out of sklearn, doesn't have transparent support for online learning, but that's by default built into probabilistic methods. And small data problems. So frequently, you're doing analysis where data is expensive, where it takes manual effort in order to evaluate what you've done. And that's not a world where you've got big data. It costs a lot of effort in order to get each individual point, so you want to maximize your support. And then once you're beyond some threshold of certainty, stop sampling, stop annotating that data. And I think that this boils down to two views of machine learning. So one is that models should be general and black box components. You should be able to, from sklearn, import model, model.fit, model.predict. That's not what this is. So John Salvatier was a core developer of PyMC3, and he has this line that black box machine learning is like BOPIT, and PyMC3 probabilistic modeling is like Legos. So whereas BOPIT is a toy that you take out of the box and it works exactly like you expect, and that's pretty much all it does. Legos is a set of tools that you use to build your own model, to reflect your system and then interrogate, crash, break down, rebuild. I tend to prefer the second type. So these models are built to mirror the problem at hand from its first principles. And just to close, there's an area of research in Bayesian deep learning. So deep learning, some would say, is the ultimate black box model. You encode very complex systems, you can download them directly and apply them to your problem with no transparency into what's happening. But an active area of research is applying Bayesian methods to deep learning models. And the core strength there is the support for uncertainty. So this comes from a blog post by Alex Kendall, who's a researcher at Cambridge in computer vision. So the left image here is the input to a depth measuring neural network. The middle image is the output of that network. So it's saying the red is closer, the blue is further away. And the far right is the uncertainty, so the standard deviation of the prediction. So by fitting distributions to model weights and propagating through to the predictions from that model, we can actually say, here's where we are not sure about our prediction. It's not a binary yes/no. It's not some pure regressed value. It is. It has this range of possible outputs, which there's a lot of examples out there, but that can save lives. There was I think a situation where a Tesla self-driving vehicle crashed into the back of a semi-truck. And when you go back to using the model, the machine computer vision model that it was using, and propagate through uncertainty on the weights of that model, you can see that it confused the back of that semi-truck with the sky. And it was pretty certain that it was unsure. But when you're only making a binary or a regression prediction, and you don't have support for uncertainty, bad things like that can happen. And that's all. So I think I have a few minutes for questions.
Yeah. More than 6 minutes of questions.
Yeah.
Stunned silence.
So when you talk about Bayesian deep learning, what about instead of modeling just the mean and standard deviation, if you just try to parameterize those distributions with neural networks? Do you see that as a possible solution?
Yeah, so the question is, could you just parameterize the distributions of the neural network?
Yeah.
So I'm not sure I follow that. Do you mean fit distributions to the weights that the neural network is fitting?
So I guess like right now, in kind of all your models, you're tracking like the mean and standard deviation, trying to get posteriors for those.
Right.
Would you just be able to parameterize the distribution itself with the neural network?
So the trick there is you have to have a distribution to sample from. So if all you're doing is fitting point estimates for the weights of a neural network, then all you're going to get is point estimate outputs. But if instead you fit a distribution to those weights, so you say the weight matrix for this hidden layer is no longer a set of points, it's a set of distributions, which are each parameterized according to some parameters, then you can do what you're talking about, right? Because you have support for uncertainty and that propagates through the entire model. So rather than it being like a point-wise matrix multiplication, now you've got distributions that are summarized by points, and you can then sample from those and see, well, based on this outcome and the uncertainty with each of the components that led to that outcome, how uncertain are we? Does that make sense?
Yeah.
Yeah, it's a really hot area of research. There's a MIPS workshop next month, probably the premier machine learning conference in the world. So this area is really hot. I would encourage you to engage deeper.
I have a question about, so you had mentioned when your data is expensive, you can keep sampling it until you get enough certainty. What if, can you use the model to infer the data that has yet to be, in this case, let's say labeled? Which data, if it was labeled, would improve the model the most? So say like you have 100 data points that you could in theory label, but say 10 of them would add the most to your model. Is there a way of inferring that? Could you like predict over each of those cases and see which one has the least certainty?
Yeah.
That one too?
So one of the core assumptions here is that the data that you're predicting over is their IID. So they're independently and identically distributed. So saying we want this value to be at this edge of the distribution, and we're going to predict where that comes, by that definition is not possible, because you're saying that no point has any bearing on any other point. Yeah, but you could certainly identify, well, we would learn more if we found a value at the tail end of this distribution. The trouble would be predicting when that's going to occur.
Yeah. Could you like estimate that by the uncertainty in the prediction in that point? So like if your model has less certainty in the point, let's say, is at the tail, if you would label that and then learn on that, would that provide more information to your model than you say have another point that it predicts is more certain, like maybe distributed around the mean where you already have a lot of sampling?
I think if you include, say, very far off tail points back into your training data set, that's obviously going to lead you to either better estimates of your uncertainty or better predictions if you try to move sort of the weight of the curve leftward, so to speak. But as far as saying at which point I'm going to learn from the most, I think the best you can hope for is that you widen your uncertainty bounds. So if you say, I'm this far uncertain, you get lots of points that are way outside of your distribution, then I think that tells you that your uncertainty may not be correct. And so perhaps you've got biased sample data. But yeah, ideally, if you're doing an online sort of model evaluation like the one that I talked about, that would be brought in to expand your uncertainty estimate by default. So you'd be saying, well, now, including these values, which are much wider, I'm this uncertain. I'm much less certain in my predictions. Yeah.
How do you handle the bridge you have to cross from deep learning and statistical tribe terminology to the business owner, organizational business owner vocabulary when you're talking about the fact that they don't trust Bayesian, and they've only heard that word because of mistakes in the past. And
Yeah.
you're talking about introducing uncertainty, at least making it more transparent, and they're saying, well, it's not a transparent tool.
So my favorite example of this is the confidence interval. So almost any executive, when they're evaluating a model or trying to say, well, you should do this because it's going to have this positive outcome, is going to say, well, what's your confidence? And the intuitive explanation to a business person for a confidence interval from a frequentist statistics perspective is really difficult. It's a hard thing to explain to business folks to say, well, if we were to run this example this many times, then we expect that the long run average of those observations would fall within this range, X% of the time.
Should you shift that to something else?
Yeah, so Bayesian credibility interval has the interpretation that I am this confident this is going to occur, and that's it. So I think it's a much more intuitive way to go from Bayesian speak to manager speak, because you're not having to couch it in statistical long-run averages. You're saying, based on the data that we've observed in the model that we've laid out, here is our confidence.
All right, that's all the time we have. Another round of applause for Zach.